Hey, this is Porg O'Neill. This is my video presentation for my final year project. My final year project was using genetic algorithms to play Atari video games, specifically the Atari 2600 console. The reason that I did this was, one, I'm interested in artificial intelligence, and genetic algorithms seems like a interesting topic to research. And the reason that we chose Atari games was because Atari games are fairly simple because they're old, and we know how to succeed in it. It's easy to measure how well we're doing. So genetic algorithms are an implementation of the Darwinian survival of the fittest thinking. So if we take a quick look at some of the diagrams here, some of the main parts of genetic algorithms is how we actually bring about new generations. So one of these is crossover. So here what we see is two parent genomes. When they're bred together, the new child genome will inherit parts of both the parents. So this is how we try to breed good traits and good genetics through generations. So here we just see two bytes. One is all zeros, one is all ones, and when they breed together we get a mix of ones and zeros. And the other main part, one of the other main parts, is how mutation is applied. So what mutation does is basically it makes sure that everything stays diverse. So basically at every point when we introduce a new child, there's a chance that one of the bits might randomly mutate. So this is kept fairly low, because we don't want it getting too diverse, or else basically the population ends up being completely random. But at the same time, we can't let it be too low, or else we can end up plateauing and ending up with very limited population. So the first thing that I did when I was implementing this project is I broke it up into iterations, and my first iteration was working with a hard-coded AI, basically get familiar with the toolset that I was going to use. So the toolset that I used was the Arcade Learning Environment. The Arcade Learning Environment is a framework on top of the Stella Atari emulator. So it has a bunch of handy APIs, allows you to access a lot of information. So I'm just going to zoom in on my diagrams here. So basically what I did to make the hard-coded AI was I used the Python imaging library to search for where our paddle and our ball is there. So the player paddle in this diagram is the green paddle, and then the little white kind of square item is our ball. And what I did to get that was, first of all, I would cut it up into a region and make the frame a bit smaller, get rid of that excess stuff that we didn't need, and the score and the top bar there. And once I'd done that, that's when I actually searched to see if I could find these paddles, or these pixels. Once the pixels are found, I was able to use that to decide where the height for the ball and the paddle was. And when the ball fell out of the range that I wanted it to be in relation to the height of the paddle, I'd move the paddle in relation to that. And here we just show, just when I'm debugging, the way I did it was I'd look for the color of the pixels, and here I've just drawn a little red box around where it's actually found the pixels. It's a little bit off there, but that's pretty much it. That got us the Y value, the height value that we needed to track it. Now using that, it was quite successful. A little bit slow, but it did the job. It was quite intensive because of the image processing. So what we'll do is we can run it here. And once we're up and running, if we look here at the gameplay, we can see the movement is a little bit erratic due to it waiting for the ball to go out of range, and then it moves. But most of the time, our paddle will hit the ball, and in any game that I ran, the player always won. It may have missed a ball or two, but most of the time it got all the balls. And the second iteration that I did was I did an iteration of the NEAT algorithm. So the NEAT algorithm is neuroevolution of augmenting topologies, and it's a method using genetic algorithms to evolve artificial neural networks. So this method uses neural networks, so it starts off not the greatest, and then it builds up. So because we have to train it for quite a long time, I'm going to use some pre-made videos here just to show what the kind of behavior we get is after we've trained it. So here, if we run this here, now it's going to start from the middle of the game, but if we go back to the start, so we should see a game start here. So we see that it moves up here, builds a strategy where it collects the bonuses here, and then makes a very swift move to the top, where there's a stream of little collectibles there, and that's how that reacted in the game Asterix. So it learned to come up here and get, that's when I ran it, that was the best score that I got. And then the other iteration that I did was an iteration of my own algorithm, my custom algorithm. So here, the way I encoded the genomes was it was just basically arrays of controller input, and so this way it was a lot faster to actually evaluate and to run. And also from the get-go, you could have successful genomes. So if we look here, now the thing with this one is we do see that it's actually a lot more erratic in its behavior. It's jumping up and down, it's continually moving. But I did find that both of these methods were actually successful.